lecture 15. I hope you had a little time to catch up with the course in this little break. You can see the screen, right? Everything okay?
Yes.
Let me check how many of us are here before I make some comments. Okay, we are a good crowd. So a number of you wrote to me, not as many as I would have regarding the exam. I got a few of you saying that they prefer no take home. If you do not write to me, I will assume that you like the take home. And we are gonna do a sort of democratic vote. I can't give 2 exams. I wouldn't know how to grade you if I gave 2 different exams. So if majority wants to take home, I'm sorry for those of you that may not like the idea. Although strictly speaking, I don't understand how a non-take home exam could help you. You would have to study for that. It can't be that this is a very hard course. I don't even know how one studies for the standard model. That's why I give a take home. I, for one, wouldn't know how to study. Whereas stay home, you don't have to study. You get these problems and you just work on them. But anyway, so if you have strong feelings, write to me. By the way, there was also someone wrote. I'm going to respond to you guys. Just want to see how others feel. They would be nice to have a loop study in the course. I'm not going to be able to do that during the lectures. It's not part of what I'm supposed to do here. But there'll be surely either a homework or a take-home exam. There will be one loop so that we can discuss it. And I'll give you a finite loop so that there is no problem over a normalization, just a straightforward, for integral. Any questions, comments? Regarding the course or exam? What I want to talk about, what is sort of becoming the part of the standard model, it surely wasn't there in the beginning, and that's the crucial, if you wish, incompleteness of the standard model. The central issue today, the door, I would argue, not just a door to new physics, neutrino mass. Why is it so important? Why is it so crucial? Why is the core of what we are after in studying the new physics? Because simply standard model predicts neutrino mass 0, but experiment tells us, implying that standard model is not a complete theory. It is not wrong. It was not supposed to be theory of neutrino mass, just the way that Newton is not wrong. Newton can never be wrong. But Newton theory is not complete in that sense. But this is great. This is what we love. We have loved great theories of nature that are not complete. Because this is arguably then, I don't know why majority of people, when you look at the people, the spokespersons for our field, they say nonsense. They will tell you that it's the Higgs mass, which works perfectly. They will give you all kinds of argument that it's some hierarchy problem or whatnot. But obviously, the door, okay? This is, I don't know why you would debate mass. Neutrino mass is arguably the door to new physics. Any sensible person, where are you gonna look? Where the theory did not do its job, where it was incomplete. But we have to understand, so this is very important, this is crucial. So this lecture is kind of, well, every lecture is important. You know, I've tried to argue we are covering here only the essence of the field theory application to particle physics. But this, for those of you that want to do physics beyond the standard model, literally that think that you want to do physics beyond the standard model, and then you want to really understand natural phenomena, here is your chance to think where the handle could be. Now, why do we say that neutrino mass is zero? Let's try to understand that. In order to understand the neutrino mass, we have to step back. Let's step back. As usual, when you have to address something new, you step back and try to understand the core of what you claim was the prediction. And that means, let's think about Fermion masses once again. In order to think about the Fermion mass, you take the particles that you know and love best, electron. What about electron mass? Sorry. So what about electron mass?
I found this on the web.
That electron mass, let me write like this, has this form. That's for Dirac taught us, which we said is EL bar ER plus ER bar ER. So let's call this Dirac type mass term. What is characteristic of this term? There are two aspects of this term. One, it is Lorentz invariant, obviously. You check that. And it is also U1 electromagnetism invariant. Now, this is a thing that is very interesting, the Lorentz invariant. Is this the only Lorentz invariant mass term? That's what people thought when Dirac wrote his famous Lagrangian or equation. So we have a question. Lorentz invariant mass. Is this the only Lorentz invariant? You know this. Someone should help me.
We can consider Lorentz invariant quantity by, oh, I'm sorry. I was thinking about the SU2 invariant quantities.
No, forget SU2. I don't even worry. SU2 is broken. I'm just thinking now in nature. I'm not thinking about the standard model. I'm stepping back really to the core of it all. You know, the only symmetry for us, there is color, right? But I'm not talking about strong interactions. I'm talking about the electron. So for you and me, there is only U1 symmetry in nature. When we have to think of weak interactions, we build this SU2 cross U1, we broke it spontaneously. because we know that the only unbroken symmetry is U1. But the crucial role in all of this is played by Lorentz. That's somehow a central thing that we have to understand separately. We have to understand every essential symmetry in its own glory. What was the homework one? Or better to say, if I have a psi L wave function, let's not even think of the electron. This is some left-handed spinner. Which will be a projector. If you like to think of the four-component spinner, there will be a projector. On what we call left. And that, remember, with our conventions, is just a two-component spinner. UL is just what we would call the spinner under rotations. Spinner of quantum mechanics, of course, it's also spinner under boosts. Okay, this is a two-component. And UL transforms as e to the I sigma over 2, as if it was a just SU2 rotation spinner. And then he had this famous combination of rotations, this you knew. I remember you helping me in Boost. Boost is very similar rotations, but the generators are not Hermitian. There is this factor Y here. That's the only difference. In quantum mechanics, how do you form invariant spin zero state? When you have some spinner which has up and down component.
We take antisymmetric combination.
This is invariant. This is our spin equals 0. But notice, because it's transpose, you see immediately that UL transpose I sigma to UL is invariant under Lorentz. Just call theta plus I phi, or it's some alpha if you wish, complex. Who cares that it's complex? There is a transpose here. So U transpose I sigma to UL goes into UL transpose e to the I sigma transpose over 2 times alpha. You see? Alpha complex or not is irrelevant for me because I don't have to take a star. E to the I sigma over 2 times alpha UL. But this is UL transpose. I go commute I sigma 2. This will change the signs and you will get minus I sigma over 2 times alpha times E to the I sigma over 2 times alpha UL. This is manifestly invariant. You can write, of course, you can recognize those of you that remember a little bit charge conjugation. You can see immediately that I sigma 2 UL is simply psi L transpose C psi L, because C is basically I sigma 2. This is our charge conjugation. So in other words, there is what we called a Majorana mass term. In 1928, in his classic work, Earth-Shattering, Dirac finds this magical thing. Some almost, in his last paper before disappearing, a great Italian genius, write in 1937, a Majorana mass term. He realizes, and that has earth-shattering consequences, that this is, we will call it of Majorana type. I don't need left and right. I can just use psi L transpose C psi L. Of course, if that is a mass term, I can also have this if there is a right-handed. It doesn't matter. Left or right are interchangeable, okay? This is very important. We'll talk about physical consequences. It has a dramatic impact for neutrino mass and the associated physics. This is also Lorentz invariant. Just to remind you, if you have a Dirac mass term, which requires psi L and psi R, then you write a Dirac spinor, because mass term unifies left and right as psi L, psi right. And remember with our conventions that some 4-component spinor where UL and UR are completely independent. In my Rana case, when I have only psi L, and I like to have a 4-component thing, I'm used to it, I can still construct it. It's called psi Majorana. It's psi L. There is always, remember, I keep teaching you from the first day, if there is a left-handed spinor, there is a right-handed anti-spinor. This is right-handed. We checked explicitly. So psi Majorana is psi L plus I gamma 2 psi L star. It is also 4-component, but very funny. It has only 2-component independent spinor. The right-handed guy is made out of left-handed guy. So if you wish Majorana spinor, this is called the Majorana spinor. This, of course, is called a Dirac spinner, as you know. A Majorana spinner or a Majorana particle. Notice this, it's half-time particle plus half-time antiparticle. Precisely half-time, half. It's psi L plus psi L tran. One describes the particle, the other is, it's a very strange state in Majorana spinner. The reason I wrote it, what I mean by that, so in the summary, Dirac guy, psi bar psi, in simply psi L bar, psi R, plus psi R bar, psi L. Majorana spinner, psi Dirac, let's say like this, psi M bar, psi M. You see psi M bar, what is psi M bar? This is psi L bar plus C psi L bar transpose everything bar, psi L plus C psi L bar transpose. Notice, as you know, psi L bar, psi L is 0, just like in the Dirac case. So this is C psi L bar transpose bar psi L plus C psi L bar transpose. No, sorry, I don't want that. Psi L bar C psi L bar transpose. The first term, it takes some plane width. Let's just indicate what is psi L bar. That's psi L dagger, gamma 0, transpose psi L. The second term is just Hermitian conjugate, obviously. This is C, gamma 0, psi L star. And then bar, you take a dagger and gamma 0 psi L plus Hermitian conjugate. Please follow me so that I don't make a mistake. So I take a dagger, this becomes psi L transpose, gamma 0, C dagger, gamma 0 psi L plus Hermitian conjugate. This is psi L transpose. Gamma 0 goes through this by changing sign because gamma 0 anti-commutes. So I will get minus C dagger, gamma 0 psi L plus Hermitian conjugate. This is psi L transpose minus C dagger, psi L plus Hermitian conjugate. Gamma 0 square is 1. And this is, let me write nicely separately, psi L transpose C psi L plus Hermitian conjugate, since C dagger is minus C. So the famous Majorana mass term, which of course must be Hermitian, the one that we wrote above, plus Hermitian conjugate, can be written precisely the same way as Dirac. Only the Majorana spinner is very different. Okay, this what we call the Majorana mass. So you see, you can think the following. you can think the following. That there is something funny in the Majorana mass term. You see the Dirac mass term. The Dirac mass term takes the antiparticle and combines with the particle. This is how it preserves charge, for example. But notice Majorana mass term, what it does. Particle, particle. This is very different. Or if you wish, a Majorana spinor that corresponds to Majorana mass term is half particle and half antiparticle. We should help you answer the question, why I do not write the following mass term. Why doesn't Dirac write this mass term? Why don't we give credit to Dirac? Tell me. For the electron. Why not? After all, this is Lorentz invariant.
I think it's because we don't see electron changing to its antiparticle.
Right, which is what? We have a name for that?
Positron.
We have a name for that. That's called charge conservation. By this, I mean electromagnetic charge conservation. EL transpose CL, this manifestly breaks U1 electromagnetism. Remember, after U1, under U1, EL and R transform the same in sum e to the I alpha ELR. And the charge conservation is so good. If you wish, I can call this is M electron Majorana. What I mean by that, experimentally, ME Majorana over ME Dirac is less than 10 to the minus 20 at least. This is what I mean by the charge conservation. It's really in the standard model, we wouldn't get it. If I use the Higgs mechanism, by the way, just to step back, in the standard model, which is the SU2 cross U1 H series plus Higgs doublet. Okay, here what is nice, ME Majorana is equal to 0. Because I have a left-handed doublet. Right-handed singlet. So through the Higgs, the only mass term I can write was LL bar, remember phi ER, because I have a doublet and doublet, doublet and doublet. This is okay, but for example, this is not. Why is this not okay? What does it break?
Charge conservation.
Yeah, I mean, in SU2 cross U1, if you wish, breaks U1 hypercharge. And that means that it breaks charge. This is important. Similarly, of course, the EL term in a similar manner would break U1 and even SU2. Good. Neutrino. So now we equip. You see, we had to step back and think carefully about what mass really is. What is the mass? What is the physically allowed mass? And what is the mass in the standard model? We have two fundamental questions, okay? First, in order to understand the standard model better, a second, in order to know how to proceed once we see that the standard model is not complete. So this is the standard model. To be specific, there is no new R. This is our standard model. It's all here. So obviously, no Dirac. New L bar, new R cannot be there because there is no new R. We are talking about the standard model that describes particles that have been seen in nature. And there is no new R by construction. What about Majorana? Let me be more specific. This is the mass term of Majorana. What about this? Look how big I wrote it. I'm giving it a great importance. Can I write this? This is a crucial question because if I claim that neutrino is massless, and you should have asked me, I thought I've said it's obvious because this is obvious. This part is obvious. This is trivial. It's a tautology. I can't even talk about Dirac because there is no Reich and neutrino. But this is not obvious. Is this allowed? A few minutes ago, you told me about the electron. Why is this different?
It should again break U1.
Sorry?
It breaks U1. Why?
U1? You should be specific. Which U1?
Yeah, hypercharge.
Hypercharge. Thank you. I know you meant well, but you must learn U1 hypercharge. When I have more than one electromagnetic, it doesn't break U1 electromagnetic charge. I could write this mass term if I was allowed to break the standard model symmetry, but I cannot. I'm forced to have the Higgs mechanism. Without the Higgs mechanism, there is no standard model. You cannot compute anything. There are no loops, anything that would allow you to make comparison with the experiment. So this is the standard model. It's an SU2 cross U1 symmetric theory plus a Higgs mechanism. By the way, this term, you may see, breaks also another symmetry. Which one?
ACU2?
Yes, obviously. Notice that when I write my doublet, then T3 acting on UL, of course, is non-zero, it's 1/2. So these terms has T3, which is a half, twice and a half, this is 1. Lagrangian cannot carry, you know, what we call weak isospin or whatever, these SU2 numbers, okay? This is different from 0. Well, obviously, because you can think about that. You cannot write that because there is no new L. There is only LL. There is no sense even to speak before you break the symmetry of new L. That happens later when we manage to, through Yukawa interactions, give electron a mass and couple it to the photon. We have to break the symmetry, so there is a massless photon, there is only LL. So we are not allowed to do that. This is why we say that M nu is 0 in the standard model. This is equivalent to saying that M nu Dirac is 0, no nu R. M nu Majorana is 0. This is the prediction because he would break SU2 and U1. Just wanted to convince you. It's basically there, but it's good to once again to be completely clear about the nature of mass and the nature of the standard model symmetry break. Neutrino is massless. This is a great success of the standard model. There is often a confusion because people say, oh, I don't know, is that really by construction or something? No, this is a prediction of the standard model. Because the standard model is a minimal SU2 cross U1 case here. So the Higgs sector is minimal. And that means the phi is the doublet. I don't have to write. D may look like Dirac minimal. There is just phi doublet. This is the essence of our claim. So now we are going to have a serious dilemma. The question that you and I face here and everybody else in the field, what next? Before I go on, notice the following. So let's go again back to the standard model. So once again, nu E, L, and ER. The difference between neutrino and electron, the main difference in the weak interaction theory is that nu is neutral, E is charged. That's the main difference. But remember, but charged particles means no Majorana mass. So this is why there is sort of a prejudice that most of us share in the field, that Majorana could explain why M neutrino is so much smaller than M electron. This is the hope. In the Dirac case, if neutrino is a Dirac particle like electron, it will be hard to understand why two particles that are siblings, neutrino and electron, W cannot even distinguish them, have orders of magnitude different masses. I don't mean just a small difference like muon being, I don't know, 100 times heavier than the electron. This is a dramatic thing. What I mean is that mu is less than 1,000,000 times, and they live together in the same multiplet. They are not different generations. They are siblings. I'm saying this for the following reason. Because imagine that I say, so let me imagine, this is the work of Weinberg in 1979. Weinberg, and this is not how historically took place, but it's illustrative. Weinberg says, imagine, however, that these are really the states. In other words, that I have only standard model states. Maybe I have some very, very heavy states, of course. You know, I may have a grand unified theory even in my hands. It's not that Weinberg believes that the standard model is the last word. Far from that. Plus some very heavy states. I don't know what heavy states are. I can't talk about them. So Weinberg says something very interesting. When you have very heavy states, then Weinberg says, we should imitate Fermi. What I mean by that, remember how it all started. Fermi, 1934, beginning of new physics. There was just electromagnetism before. Says, I have this weak interaction physics. I have to describe some funny process. Neutron decays into a proton plus the electron. I believe that Pauli is right, he says. And I can write now the three-body decay. I don't know, he says, what is, there must be some heavy particles, of course. Someone will be a messenger of this force. Something is going to happen, but I don't know what it is. So Fermi says, let me assume only above particles. Then I must write what we call effective theory. I will not write a fundamental Lagrangian renormalizable. And that is famous Fermi effective Lagrangian, which is G Fermi. There was some square root of 2, J mu weak current. It's an effective theory. It has a dimensionful coupling. Okay. It's very similar the way Newton says about gravity some 4 centuries before. There must be a messenger, says Newton, which is sort of funny because for centuries people taught us that Newton was that a genius was a fool at the same time, that he believed that forces are instantaneous. No, Newton says, I'm sure there's a messenger, but I don't know how to describe it. So I'll write the effective theory. So Weinberg says, I'll do the same. It's a beautiful paper in which he studies a number of new physical processes that violate baryon number and lepton number. But it doesn't matter. For us, it's just neutrino. So he says, so by analogy, says Weinberg, I will believe that there is only a left-handed electron, neutrino, and so the only mass term I can write is this. Simply, there is nothing else I can write if I believe that these are the only particles. But this is what he says, but it must be Lorentz plus standard model invariant. This term. Now, this is Lorentz invariant. That checks. What about standard model? It's not, you just told me. It breaks U1 hypercharge. So what should I add? What fields can I add here to restore hypercharge? I must add something here. And SU2 to restore standard model symmetry. Or you can think of hypercharge. Remember, in standard model, you have this. Let me write once again to help you. You have ER. What else you have? You have this. So what should I add here? Which field? Let's think of hypercharge. This is -1 and -1. But I need to add to 0. You got to help me. We're building this together. This is just group theory. I need to add fields that carry hypercharge. But I don't want to break Lorentz invariant. So what should I add here? Scalar fields. I can only add a scalar field, otherwise I will break Lorentz invariant. I already Lorentz invariant. So which scalar field should I put here? Any help? Which scalar field?
Phi that you topic.
Phi?
No.
What
Phi
did you say?
transpose phi.
Sorry? No, which field? Just tell me which field. I know how to write. Just tell me which field should I put.
The W that you wrote next to
Sorry? I
5.
can, which phi? No, there are, look, I took only neutrino. There is no lepton, the whole lepton, which is neutral. There are two fields in phi. Which one should I take?
Phi 0.
Yeah, of course. I don't want to break charge. It has hypercharge +1, remember? We had opposite. This is not good. So what should I do? 1 is not enough. Weinberg says I have to take 2. I can write this. But notice, what is the dimension of this term? Now this is 0. Look at T3. Neutrino has +½ Neutrino has +½ Phi 0 has a -½ Phi 0 has a -½ Now I got 0. You see, it checks. But what is the dimension of this term? Help me so we can take a break, please. I need my coffee. You knew dimensions. You told me you knew them.
Is it 5?
Dimension 5, thank you. You see, this is an effective Lagrangian. This is not a renormalizable term. Just like Fermi had, these were dimension 6 terms. The currents are built out of fermions. Okay, so this is not a fundamental interaction. That means it must be divided by some scale. 1 over lambda, we could call it lambda Weinberg instead of G Fermi. If you can call it lambda Weinberg if you wish, we'll think about it, what name to give it. Okay, yes, thank you. We have to think a lot about this, okay? But we should do it after the break. So if you don't have an urgent question, I'll make a break now. But if you have a question, tell me very briefly, quickly. Okay, even better. Let's think. We go back in 6 minutes at 12, 11:54. Okay, we must understand this better. We meet back at 12. So what we are discussing here is what we could call effective theory. This is what we've done, but we have to understand it back. The reason I'm doing it, because when you don't know, this is somehow the kind of fundamental approach when you don't have an underlying theory. You may actually, if you have an underlying theory, that's better. Standard model is much better than the Fermi theory. And it took some time to develop it. This is an interesting thing. I'm teaching you an effective approach because there's a sort of fundamental thing when you don't have a theory. But actually the theory of neutrino mass came before this effective one, and I'll come back to it. Well, I'll do it later, just to sort of to show you how you would reason the way Weinberg did, following the other people in the past. And I will tell you, of course, the shortcomings. The Fermi theory couldn't tell you anything about what the message is. It couldn't predict you new interactions. It just characterized the existing force, which is an important step. It will tell you something, but it's not complete. So really what I wrote here, so I wrote the mass term. I said because of dimensional reasons, I write something, well, it may look like weak. So let's not call it lambda W. Let's just write 1 over lambda. And then I wrote nu L transpose, C nu L, phi 0, phi 0. Of course, this seems correct, but this is not, this is a cheat. I have cheated a little bit. I just wanted to take us there. Why? Because there is no nu L. Instead, I must work with LL. And then I must work with phi, really, as I was actually told. But I only did the sort of naive builder's point of view. So you can tell me, aha, let's try to write down instead of these fields. You can say, oh, why not? That's easy. So just write like this, 1 over lambda. Instead of nu L, write this. You can pretend and write phi transpose. Now this seems to be this seems to be the generalization SU2 cross U1 invariant. And it is this is the SU2 singlet, as you know. SU2 checks. SU2 checks. This is how we do the singlets. We take a doublet and anti-symmetrize. So SU2 checks. And of course, hypercharge will check. Also, U1 hypercharge. But not like this. They have opposite hypercharges. So U1 hypercharge checks. Between these two, why? Because high YLL was -1, if you remember. If you don't, please check it. We discussed it repeatedly. There is something wrong with this term, though. It seems good, but there is something wrong. Who's going to help me? Phi transpose I sigma 2 phi. What's the problem with this?
Is that term 0?
Yeah. This is a scalar. This is phi plus phi 0 minus phi 0 phi plus. This is manifestly 0. So this is no good. So what should I do? What should Weinberg do back in 1979? What next? So look, I'm playing, I have a doublet, LL, y equal minus 1, and phi, y equal plus 1. They are both doublets. I can write out of two doublets, I know how to form a singlet, you agree? I can do this. Well, someone wants to help me before I start writing? Some hint?
LL transpose C psi phi.
Yes. LL transpose. C phi, you are saying. I don't need C for this. This cannot be. Phi is a scalar. You don't mean C. What you mean is I sigma 2. You agree? Do you agree?
Yes.
This is not invariant. These are two different spinors. This is perfectly SU2 invariant. This is SU2. Actually, it's even more than that. This is SU2 cross U1 invariant. But it's not Lorentz invariant. This is a Lorentz doublet. So why don't I just do the following? I can take another SU2 cross U1 invariant term. Why do I need to take it once again? Because I have to get a Lorentz singlet. In order to get a Lorentz singlet, I have to take LL twice. And one has to be a transpose, as you know, and one's no. And now, of course, I put charge conjugation as you wanted. Charge conjugation acts between L and L. Here you understand, the only guys carrying charge conjugation components is this guy, if you wish, but that you should know. And of course, I put some 1 over lambda. I found it. You helped me, you found it. Okay, we did it together. This is the famous, it's called the Weinberg. When you're Weinberg, then of course your name gets easily attached. It's Weinberg D equal 5. It's just because it's a dimension 5. Neutrino mass operator. By the way, there are two more ways of writing this D equal 5. Find them. Play with it a little bit. This may be the homework or an exam, we'll see, but this is sort of something you can play with. No, don't look in, try not to look in the books, but for literature or anyway. Now, to understand what is going on, we can always choose phi to be phi unitary, which is 0v, sorry, 0v plus h. And then we will get, because of I sigma 2, we will get only neutrino gets decoupled. So this is an effective theory. Obviously, there is 1 over lambda. This has nothing to do with the standard model. The standard model, you should think of the standard model. This is what Weinberg says, is lambda infinity limit. This means that there is some new physics. Lambda, in other words, lambda is the scale of new physics at some high energy. The idea of writing effective theory means that lambda is much bigger than MW. This is the idea. The trouble is that, notice, you have no idea what lambda is. So means you have no idea. Of scales, sizes. You don't know how heavy neutrino will be. It's just a way of parameterizing. It's not, you can't make predictions, but what you find from here is that neutrino must be Majorana. That's a very important thing. You are saying if I don't introduce new light states in the theory, whatever the new physics is, I don't care whether you like some grand unified theory or something coming from extra dimensions or whatever you like to think about. Weinberg tells you, if you do not change the light spectrum, if the states which are light, by light I mean the electroweak scale, then neutrino is Majorana and neutrino mass term. Notice this is the first statement. I should have just written this. This is 1 over lambda. No, why don't I just keep it here? We can write it. We see immediately that m nu is 1 over lambda times v squared. Why? Because the interaction is 1 over lambda, UL transpose, C in UL. And then remember I have v squared plus 2vh plus h squared. The first term will be the mass term. The second will be the Yukawa, as you know, interaction. Yukawa is the way Higgs interacts with neutrino, the leading term. And then this is small. This is some expansion. So this we can even neglect. We are always interested in the linear Higgs term, okay? So obviously from here, you get that neutrino mass is m nu. Remember that MW is G over 2V. So if lambda is very big, neutrino mass will lie much below the weak scale. In other words, this is something of order MW square over lambda. The thing that Weinberg tells you, the neutrino should be Majorana, but he doesn't help you more than that. This Weinberg's operator became a celebrated way of doing it of understanding neutrino mass, and it's not fair. It's really because you're Weinberg, because this is what Weinberg helps you to parameterize your ignorance. He tells you measure the neutrino mass, I'll tell you what lambda is. But he's not correlating to neutrino mass to any new sort of physical processing. He cannot do that, except, no, this is important. This is important, yes. Neutrino is Majorana. We have to think about what it means that neutrino is Majorana. We are going to spend a lot of time trying to understand that, okay. Notice, however, that Yukawa coupling of neutrino in the theory is given by V over lambda, right? It's the way the Higgs couples to the neutrino. That's V over lambda. So that's all order MW over lambda. But notice that that's also we can write. We can write this, how should we write? We can write it in an intelligent way. Why don't I don't really need this. Sorry, let me use the privilege and erase it. It's V over lambda, and this is V square. What should be the intelligent way of writing it?
It's M nu over M W.
Precisely, very good. It's V square over lambda, thank you, 1 over V. Which is roughly, well, we can write even precisely. Why don't we do better than that and write precisely what you said? This will be G over 2, M nu over MW. Notice this is beautiful. Remember that Yukawa electron was G over 2, ME over MW. So exactly the same expression we get. Complete analogy with all the other masses, but it's always like that. If you use the Higgs mechanism, even in the effective theory, you'll get the same ratio. Notice that unfortunately, however, M nu is what is it? It's less than 1 electron volt. MW is 100 GeV, which is roughly 10 to the 11 electron volt, so that Yukawa nu is of order of 10 to the minus 11. This is very sad. In other words, you see, we are saying that Higgs decays also, there is a Higgs decays into nu bar if there is some u, doesn't matter where the physics. Notice that lambda got cancelled. For what you told me, this is beautiful, you see, I don't care what lambda is. I have a prediction, but it's a tragic prediction. Another aspect that tells you that Weinberg's operator is not very useful because there is this decay. This is predicted independently of the theory, but the ratio of nu bar will be some number of order of 10 to the minus 22. So you have to see Higgs decaying into nothing. Neutrino is missing energy with a branching ratio of 10 to the minus. This is 0 at LHC. Or at any other machine. This is 0 for centuries. So somehow you see what the effective, so what this equal 5 effective theory does. It's a very useful language, but a useless theory because it tells you there is some new physics. At lambda. That physics somehow you integrate out, something happens in the end. And gives you neutrino mass, which you don't know, and gives you unobservable Higgs decays. Tells you basically that you have nothing to see from this theory, except, however, this is important, M nu is M nu Majorana. So we have to think, you and I, we have a nice task. What I want to do here, because this is very important, I want to do now two things, okay? I'm not sure which order. So what we have to understand, what is the physics of Majorana mass term? And also, what is the fundamental theory behind Weinberg? We have to discuss that. See, you and I are students of field theory. We are modern, we are new generation. You and I have to understand it's not enough that we have some Fermi-like theory. We won't stop there. This is why we built the standard model. Actually, we didn't, they did. And the reason I want to mention the second part is because the theory actually preceded this analysis. The theory of neutrino mass was suggested already in 1974. I'll come back to it. Well, I can mention it here. This is called the left-right symmetric theory. I'm gonna talk a bit about it. The seed ideas, it's very interesting, were actually done here at the ICTP in the summer of 73 and 74. He starts by the work of Padi and Salam. He didn't take it so seriously, okay? The people that took it more seriously were Mohapatra and I very soon, okay? This is 75 and it's 75. According to the theory, neutrino is massive, and we'll have to talk about it. The reason I want to talk about it, because left-right symmetric touches into the fundamental issue of parity violation. But before that, we want to understand what is the physics of Majorana neutrino mass. Because sort of there is something nice about what Weinberg did. And that is useful. He says, I don't care so much whether you like this, you know, there may be some kind Goran telling you that there is left-right symmetric theory, or there may be some other guy like me telling you it's a gut. Actually, I work on grand unification, so I like grand unification approach too. And someone will tell you, no, this comes from some string theory or whatever, or it doesn't matter. There is something that is generic to all of the theories that reduce to the standard model, that have the standard model mass spectrum. They will all predict the neutrino is Majorana. So what happens is that, so in other words, the physics of Majorana, this one, let's call this A, and let's call this B. And A is the fundamental step, Majorana neutrino. Remember, Majorana neutrino is the guy that is built out of the particle and antiparticle. Remember, that's equivalent. That's what Weinberg told us, that the mass term is like this. This I called Majorana mass term. There is also Hermitian conjugate, but that's all right. So what does this, if you have a Majorana mass term, you will break some symmetry. What symmetry does this break? Help me. Well, you can see, you must be able to help me. Whatever symmetry you see, why don't you just tell me what breaks what symmetries? Does it break color? Does it break charge? Electromagnetic charge? Anybody there?
No, it doesn't
No,
break any of the
okay.
two.
But it breaks what?
U1 hypercharge
Right.
and U2.
One hypercharge. It breaks SU2. It breaks U1 hypercharge. Okay, what else? But it's okay. The symmetries are broken in nature. So that's okay. No problem. I already got used to it. The W is massive and so on. SU2 symmetry is broken. Hypercharge symmetry is broken. It's broken spontaneously, but it's broken. What else? Plus some other symmetry. What is a neutrino? Is neutrino a quark?
Lepton number symmetry.
Lepton number. It breaks it by 2 units. Neutrino is a lepton. What it says, the delta L, is equivalent to saying the delta L is 2. This guy carries a lepton number. I have 2 leptons in the Lagrangian mass term. Delta L equal 2. There is a physical process. Now we have 2-9. What about physics? Can you think of some process that breaks lepton number by 2 units? Maybe Alexei mentioned it.
Neutrino is double beta decay.
Yes. There is a very interesting process with a terrible name, which is called neutrinoless. Double bet. It's often written like this: 0 neutrino, 2 bet. A terrible name for a beautiful process. Neutrinoless double beta means that 2 neutrons, double beta, go into 2 protons plus 2 electrons. Neutrinoless double beta. Notice if this is true, and let's understand it. If I look at double beta, in other words, I look at 2n going into, well, I don't have to write like this. Sorry, why am I saying? It tells me that the energy of E plus C is actually fixed. These guys basically, you know, this is some heavy nuclear decaying into some other heavy nuclear. You know, what happens is actually germanium decays into selenium plus electron. I think germanium has 74 protons and selenium 70 things, I think. You can check. This will be a typical process. And the energy of the electrons would be fixed. So if you plot the distribution of the two electrons as a function of energy, it will be fixed at some number. It's going to look like this. You know, it's almost a straight line, some minor error, which is sort of opposite from neutrino discovery. No? Opposite from beta decay. Here, when you plotted electron energy, the distribution of electron as a function of energy, instead of having a fixed energy, it looked like this. You had the distribution energy wide because neutrino took a lot of energy. So the electron couldn't take all of the energy, and that's how you made a discovery. Okay, this is a discovery of neutrino, in a sense. Discovery, sort of. It tells you that there is a new particle taking the energy. Here it should be the opposite. It's kind of ironic if this is true. And the way it developed, we'll have time to talk about it. I'll just sort of finish in a few minutes, but I still have a few minutes. So just to tell you, you know, we have beta decay. Beta decay, neutron decaying into electron plus proton plus antineutrino, typical process. What may happen, however, this is Maria Geppert-Meyer in 1935 says, well, it may happen that this cannot take place. For example, germanium is supposed to decay into arsenic plus electron plus antineutrino, 74, 75. But mass of the arsenic is bigger than mass of the germanium. The daughter nucleus may be heavier, so this cannot take place. Then she says, what may happen is a double beta decay. Germanium may decay into selenium, she says, plus electron, plus electron, plus antineutrino, plus antineutrino. This is called double beta. And this is okay because selenium is lighter. Of course, it takes a lot of time for this to happen simultaneously. It's huge. It's the longest measured lifetime. It's 10 to the 21 years because you need a simultaneous probability for two of neutrons to take place inside the nucleus. It's a very small probability process. This has been measured. So how does it look? I have a neutron decaying into a proton. These are, of course, quarks for us, but let's just go back to old days. W minus coming out here, give me an electron going out, and neutrino entering or antineutrino going out. Neutron. There is another neutron watching this, doing the same thing. Emitting W minus, that gives me an electron and an antineutrino or neutrino entering. This is the double beta process of. So how do I get neutrinoless double beta process from here? How do we get this? Well, remember, neutrino Majorana mass term looks like this. Let me just remind you, sorry, before to do that. When we write the Dirac mass term, psi bar psi, which is like E bar E for the electron, we are saying that electron keeps propagating, if you wish, the fermionic line. You often depict like this. This is called mass insertion, just to tell you that we are going through the mass term. But E bar means electron is going out, and E means electron is coming in. So if you are going through the mass term, call this M Dirac, then you depict it like this. This is just telling you that you have a psi bar psi term. If you have a Majorana mass term, it looks like this: nu transpose C nu. There is a chirality, but let me not worry about it. There is also Hermitian conjugate. So how this one look like? Neutrino entering, but neutrino entering also. You see, you break the. This is the Majorana mass term. And this one will look opposite. Neutrino will go out, and neutrino goes out. It's a Hermitian conjugate. I mean, I can write it for you if you wish. Why not? I didn't write it before, so I can write it now. It's nu dagger, C dagger, nu star. It's twice going out. Notice this dagger. Neutrino going out, neutrino going out. This is the same Majorana mass insertion. You understand this, I hope. It tells you that Majorana mass term breaks the lepton number, breaks the fermion number. It breaks the fermionic line. This is the way we capture. We want to capture its fundamental property. It breaks the fermionic line by 2 units, okay? And this is how you depict it. And this is how Feynman would draw your Dirac mass term, the electron mass term, which of course does not break the lepton number. It doesn't break the fermion number. It doesn't break the electron number, because electron stays electron. Okay, is this clear, please? I'm pausing just to see if something is bugging you. So how do I connect this? Well, it's very clear. This will go through neutrino Majorana mass term. This is 0 nu2, but the other process was trivial. This was noticed by Racah. This was not Majorana himself, but immediately after Majorana, Racah, Italian physicist, maybe not so clearly, and Furi, the Furi theorem in QED in 1938 writes a very clear paper that if neutrino is Majorana particle, you will get neutrino as double beta decay. This is just telling you that you are going through the mass term. Right, I'm breaking the fermionic line, which tells you that the amplitude for neutrino is double beta decay coming from neutrino, Majorana, from Majorana neutrino is proportional. It's given by, I have twice the Fermi interaction. And I'm going through the propagator. So what I have is M nu Majorana by p squared. There is, of course, p slash, but you cannot go through p slash. You can forget it. You must go through the Majorana mass term. Majorana mass is very small. So you go through something like Majorana mass term. This is very important. By the way, just for you to want to know, P is the virtual momentum of neutrino. And for the nuclei in question, it's about 100 MeV. It has been measured, it's about 100 MeV. We can talk about the numbers and so on. What we can say is that this process has never been seen. Unfortunately, everybody's looking for this process. This is now holy grail of neutrino physics. Most of the experiments, there are beautiful experiments in the Apennine Italian mountains, about an hour and a half north of Rome. There is the Central American underground, Italian underground laboratory called Gran Sasso. It's called the, that's really a great experiment, Laboratori Nazionali, National Laboratory of Gran Sasso. Gran Sasso is a beautiful mountain. There is a national park there. Where one can do great skiing, among other things. And this, unfortunately, has been never seen. The limit is now fantastic. There has been the last experiment putting a limit is Gerda. But there are tens of experiments. The whole world is looking for this great thing, you know, the magical thing that you could have a particle which is half particle, half antiparticle. That, of course, means that the amplitude is small. And that means that there is an upper limit on neutrino Majorana mass. And here the experts will tell you, I'm going to cite it as 1 electron volt. But now most people, there is nuclear physics involved, and I am not an expert. I cannot talk with authority and passion. Most people will tell you that the number actually is smaller. But for you and I, this may be enough. We should talk a little bit more about neutrino math. I think this will be a good time to stop here. I won't stop talking about the subject of neutrino mass. I need at least 1 or 2 lectures because this is essential for us. We should say a little bit more about other experiments of neutrino mass. But I hope you understood this. For me, for this process to take place, you must go through neutrino mass if that's the only source of lepton number violation, which according to Weinberg would be the only source. Nothing else remained. All we got from Weinberg interaction. This is believing in a effective theory the way he wrote. Unfortunately, this effective theory says, well, forget everything else. You have maybe new Higgs decays and so on, but you'll never observe them. What you could observe is neutrinoless double beta decay. That you could. I finished on time. I have a few minutes if you guys have questions, comments, perplexions, thoughts, objections. See how beautiful the process is. You get electrons out of nothing, really. You know, these are nuclei decaying. And if this is true, we will finally separate the electron from the antineutrino, which from now, you could never get just the electron, okay? Okay. If this is it, I wish you a nice afternoon, and I see you tomorrow. Okay.
Thank you.
Thank you.
Yeah. See you.